be obsolete, but it was 10 years of arguing from one way and another way. This is the thing that I also experienced in University of Illinois when on the job interviews you have to mention your wildest idea or your dream, and then you have to describe, Dregemer suggested that, how the world will be changed 10 years from now. And many people collapsed. It was simply terrible, and they resigned from taking that job because it's a very big thing. Quantum calculations and quantum experiments on the life processes is a very big thing. Holger, do you agree? It is more on the theoretical. This is more on the calculation level. Holger will be rightfully very skeptical, but Holger would like to discuss this quantum life, and and you want to hear about that?
Yes.
Yeah, but I mean, this is where I'm very conservative. But I say that calculation is a big thing. To see a ligand going into a receptor. It happens in neurons. Some people go crazy, some people are not crazy, and it's very much dependent, and some get Alzheimer's, and then it cannot happen so much. This ligand receptor, this drug molecule receptor is an essential thing. I mean, and we didn't believe it before. And that, I say, is quantum mechanics.
Good. What does Holger say? I want to hear Holger's opinion about
You
that.
stress so much quantum mechanics, and you're probably right that if you want to do any good calculation, there are so many small quantum corrections. You cannot calculate the shape of the molecule or so without including quantum mechanics.
See, now we discuss, because that is exactly what saves us. What saves us, contrary to all these multi-universes that essentially could die off by this quantum fluctuation, now people don't believe so much anymore in the many-world interpretation of quantum mechanics and so on. But what I would say is that it is the calculations are much easier if you have something, a molecular structure is converging or not converging. If it converges, it is a quite unique structure. I would say much more than in molecular mechanics, where you're sitting with all these fluctuations and temperature fluctuations that you can avoid in these Hartree-Fock, at least Hartree-Fock calculations, and you get a higher uniqueness. Exactly against what Holger said.
Did he? Yeah.
No.
I don't know. I mean, I think in realistic conditions you have temperatures on your molecules, so you cannot by doing a Hartree-Fock and ignoring the temperature, you can do a unique solution which is your ground state. But if there is an excitation possibility, then of course if you heat it up to 37 degrees or whatever, then it will begin to oscillate anyway. That is the physical situation. Strictly speaking, you would probably be interested in making your calculations in a mixture of finite temperature, but I suppose that it's hard enough to do Hartree-Fock. That you better stay at the ground state.
But so that's a big thing. That's a big thing. And what you say, Holger, is that the calculations I so much like to do on biomolecules, I should be careful, because you say, I say there's no temperature, but anyway, there are thermal fluctuations beside the quantum fluctuations, even especially if it is proteins. But then I say that here the numbers, the time periods are extremely crucial. A protein folding event takes usually, there are some fast ones, but usually it takes about a second or 10 seconds. And therefore quantum fluctuations can often be very large exchange of energies, or very much very energetic. That one goes on in, I would say, nanoseconds and something. But quantum fluctuations, first of all, are not so big in. They don't involve whole side chains like thermal fluctuations. So they go on in femtoseconds, and they are. I claim they are averaged out. Yeah, and therefore they make. But then you say, but you cannot avoid the thermal. No, I cannot avoid, and it's really a problem. We do it on zero temperature, and that's doubtful itself. Yes.
Yeah, but that's probably just an approximation.
Yeah, that's an approximation.
But if you wanted, I suppose you could do it also on temperature.
Yeah.
It might not be so terribly more difficult once you had educated your program to do it that way.
In actual density functional theory, there are actually scales one can put on. I like more the ab initio things, but certainly one can put some temperature on. But it is very important here with the time scale that it is quantum fluctuations are much a shorter time scale, and therefore it is it's something like a quantum noise. It's something that is it is on another scale than thermal fluctuations. But it's so that is. My wild thing. Now, Holger, let's talk about quantum life.
This quantum life. I don't know. I think about this quantum and so. I might say in general that we know, of course, or we believe that basically the whole of physics should be quantum in a way. I think maybe. Bohr would accuse me for being quantum fundamentalist, but it is that basically it should be quantum. And then maybe I should stress that somehow you can make several classical approximations to the same quantum theory. And if you do the right one, I think you almost always try to get rid of most of the quantum and put it into your good approximation that is classical. And therefore my suspicion is that sometimes quantum may be overestimated because it is certainly there as a basis of everything. But if you do the clever approximation by some classical way, if you do it clever enough, you might suppress the effect of quantum so much that you can describe many things classically. And perhaps you would be quite happy to also describe most of life classically, because I think it is not so good to have too much quantum sneak in.
No, but that's true, Holger. But then I come with a specific example. I come with this alcohol dehydrogenase.
Yes.
So this is a breaking down of alcohol or building up of alcohol. It goes opposite way. It is in chemistry. It can go. One way or the other in processes, and when it breaks down alcohol, it is doing tunneling, and that's tunneling of the hydride, and exactly how many percentage. But it is a quantum process that cannot go on classically.
Yes,
and it is 30% of this at least. Some people say 80%. I don't believe in that. But 30% of the chemical, the processes are strictly quantum mechanical.
Yeah, but I think that is right. When you have the tunneling effect, then you clearly must say it is quantum mechanically, because this is a quantum phenomenon that shouldn't happen. In the same way as urine shouldn't decay to alpha particles or anything. I mean, it is the same thing that forbids most of the heavy nuclei from decaying to alpha particle emission. And so it is the typical thing. So it is a quantum phenomenon.
Yeah, and then there's another thing, and this is superposition, and that's a thing, you mentioned it also, but it's certainly another thing. So classically, it is, in classical mechanics, it is the Huygens principle, it is clear, you see it in water, rings are coming and making beautiful interference patterns when you throw two stones out, but that can be more fundamental. They can go. It is so terrible that you can expand anything in something else, and therefore I would say the error of time is not so clear. I mean, you can, and it occurred to me when we describe states. Let's say. You can say a whole state is described by a state of good and a state of bad. And this is, you have some coefficients in, this is some basis vectors. This is some basis vector.
State of good and state of bad, what is that?
You can, it is some, you can call it green or red, or you can, green and red because they are complementary.
You're thinking of a superposition of two states.
Yeah. But
quantum mechanically.
Yeah. So, but you can also have the green state being a superposition of white light and the red state, and we would like to see in terms of interference that there's some action or something that happens in that is a superposition of two things that follow the other thing, or opposite. They build up a unique state. But you can, in quantum mechanics, have a decomposition of in terms of other states. You will not be able to do that in classical mechanics.
No.
Isn't it true?
Oh, of course, yes. That's only, I mean, these superpositions only make sense quantum mechanically.
Yeah.
This is a completely quantum concept. So, of course, I agree on that. Yes.
But actually, you can take the visible, the total light, and you can with a beam splitter or with something you can throw out first with a prism, and then you can throw out the red color, and then you are left with the green of the rest of it. So, but of course you cannot consider it as a superposition. Only quantum mechanically you can, but you can take. Okay. Yes. This you can, but you can always. This is in optics, and then you can do quantum optics. Yes.
Do you ever think that we get to the bottom of what life is?
Yeah. So this was the other thing. So Holger, you were a little bit astonished. So my uncle. We don't have to mention names, but my uncle asked me in one of his last years. He asked me if there's some case where there is a quantum, a single quanta, a single quantum is it called, that distinguish the life state from the death state.
Yeah.
And that I said that could be imagined on the cellular level, but not something like the Schrödinger cat. But he asked me, tell me if I can make if there's a quantum step all the way down to a single quantum of energy, and then I said that one can imagine that on the cellular level, where where some process is leading to cancer and another process is not leading to cancer. And but yet, Holger, that you were interested in it, and you are a little bit wavy about.
Yeah.
Yeah.
I think I don't know. I mean, of course, if you should be really honest, of course, when you are at the cellular level or so.
Yeah.
Then you have so much statistical mechanics and so much heat and fluctuation, and the system is so big that you may, of course, have what you are telling, that there could be one little quantum that could accidentally be the little one that could lead to the cancer cell and lead to the cancer.
Yeah.
But then they might go 10 years or 5 years before the guy dies.
Yes.
So it is a little bit similar to these butterflies which are supposed to kill a ship a week after because he whiffs with the wing and brings it up. So in the same way, of course, one little quantum could be bring up and lead to a cancer cell and lead to the death of the guy. But it is. It is perhaps not what would be what I would necessarily conceive as a question, because you could also say that if you are thinking that you have, as you say, that you basically only distinguish life and death, that's when you are on the cell level, or perhaps even groups of cells or so, that it's something that is rather big is needed to really distinguish.
Yeah, but now I say that exactly like stellar dynamics is very different from galaxies, and certainly, especially clusters of galaxies, it's a very different order of magnitude. The same with a protein and a cell. So let's go to a protein. There are some proteins that can initiate a cascade. And we must simply accept, depending on whether a certain person has a genetic, so to say, depletion, so their repair system is out of order with respect to UV light, for instance. And so then a single quantum, a single UV, a single ultraviolet light or photon can start what is called radiation damage on a protein, something that can lead to dithymine, and usually it is checked, or usually it's detected by the body and by the cellular processes, so it's clearly cleaved out, or and with plants it is done more efficient with electronic processes with this fantastic protein called photolyase. So that can be done. But if you don't have order in this photolyase, if you don't have this, then it can lead to cancer. It is simply, and we have found the path, and it's simply a single photon that can start that thing.
Yeah, maybe I'm stupid.
Yeah.
But if that photon causes an effect, is that photon then life, and the effect is death, or what?
Yeah, that photon, if that photon is not repaired somehow, if that the damage from that photon is not...
But it's still alive.
Yeah. It is something exactly like Holger...
It doesn't die.
No, it exactly like Holger says, it is done by a longer time span. But
so where is life? That's what I'm interested in.
Yeah. Where is life? Yeah, so now comes a thing, I don't like it, but no, I shouldn't say, because many people would like to buy the book in the Pacific. I mean, but there a person believes that actually very interesting with this quantum fluctuation, with this quantum evolution, that the whole life really started when there was quantum measurement. And the reason for that is that there are lots of catalysis in the universe. A lot of things are going on here and there, but when an enzyme really has to turn out a lot of products, this has to be a specific path, electronic path, that is chosen, and that needs quantum measurement is needed for that.
Okay, I think now we get so crazy.
Yeah.
I will not bring this, because this will not sell any books.
Well, I don't know.
No. Because what you're saying, in my ears, maybe I'm not duplicating what you're saying, but what you're saying is that the first measurement of quantum fluctuation was what, in the 30s or something? 30s or the 40s?
No, I'm saying it was when an enzyme decided that one electronic thing should be used instead of another electronic path. You know, this man who talks about quantum evolution.
So what is it? But that's because I'm stupid. What is a quantum measurement?
Yeah, a quantum measurement is a rearrangement so that electrons will preferably go on one path and not on the other path.
So it has nothing to do with an instrument actually measuring it?
No, but in our time it has to do with an instrument. But for early life...
What you're saying is that life started with the first quantum measurement, and then I think, what? It's crazy. That's in the 30s.
But this is, I see the point. I would say, I would also call it a quantum rearrangement.
A quantum, that I understand.
Yeah, I think in this sense it is.
Because then you say that life started in Big Bang, and even before that, or maybe before that, or at least in Big Bang. Because in Big Bang we have quantum rearrangements. We've had quantum rearrangements throughout the universe.
Yeah, but we are talking about life. We are not talking about banging of gas. I mean, spreading out explosions I mean, we are talking about life. And life.
So when did life start?
Yeah. What is life? So what is life? Life is something. Life are connected to processes that combine metabolic things like protein catalysis, which is enzymes, and it has also offsprings. I mean, this genetic code it needs, but genetic code and so on, it could happen in, people say, clay or in the soup, in the early soup. But they need one thing that I'm very interested in, and this is some quantum coherence. Yeah, that was the word I was looking for before in this microtubule. I mean, there's quantum coherence. And the quantum coherence is a little bit strange word because we know quantum fluctuations, but there has to be some coherence where enzymes decide, or when catalysis decide to favor one electronic path from another. This is what I say. So it's not something with measurement of Stern-Gerlach magnets, or seeing the spin states or whatever. We're just talking about some coherence and whether it happens or not happens. So then Holger would say, but why not classically?
Well, I think I should at least ask you in this discussion the question as to whether a quantum measurement without a genuine measuring apparatus organized essentially by human beings or somebody like that and put up to make a measurement by somehow enhancing the signal deliberately almost, does it make any sense that there is a quantum measurement in nature by accident somehow? I'm not sure whether there is. I mean, it's probably a very important question, because if you want to use quantum mechanics in a situation where you don't have your measurement apparatus, then this question would be somehow, if you answer that, it doesn't make sense.
That's why he redefined it and said quantum rearrangement.
Yeah.
It's a much better.
I mean, something. Holger. So something. Let's also talk about lasers. So I have been very much in the basement of MIT. I love to come there, and they also respect certain things I say, and I like this. This is a kind of. In a sense, paradise for me. But there was the construction of the laser, and the first CO2 laser. The question was whether it was the professor or the student, and I'm not going to mention names now, but it was something with the patent, and it was there was a surprise here 10 years ago. It was a kind of, you can also say, rearrangement here. But I mean, one was taken from the other. I mean, the student was... but anyway, the question is, it went on also in the basements of MIT. And therefore, now I ask the question, could a laser happen before we have electronic pumping and atomic pumping, where we pump it up in a certain system? Yes, it actually happens in a ruby stick. So we could imagine that actually
under natural conditions.
Yeah, it has.
Yeah.
As far as I've understood and heard, some gemstones that it's difficult to get a large piece of ruby. It's extremely difficult. But once you have it, you can also have alexandrite. You can have whatever. And they can make the laser. With ruby, it is the red laser. It is with sapphire or with blue. It's more. I don't know exactly, but I mean it's hard with the UV light. But it's you can make these. You can have these lasers in crystals, in unit crystals, or I mean. So therefore, quantum phenomena can also happen before, but you would say. There's no use of a laser in the past. I mean, yeah, but who knows? I know it's so.
Maybe had laser.
Yeah, but I mean, Holger is saying how to do a measurement.
Yeah, exactly.
Yeah, but you could perhaps say that having a laser is very close to a measurement, because you get your laser light out in some direction or another.
Yeah.
So it's a little bit like measuring one of the first photons, the direction of one of the first photons in the laser who triggers it off. Because in the laser there is this enhancement effect, that you have one little photon and it gives many.
It is certainly also that is giving a laser effect, the coherence in that sense. Of course, we talk about phase coherence also, but I mean it's certainly something that could be important in life processes. Yes, certainly you have some coherent light.
Great. So I think we are about done now, but
superconductivity is another thing. But I mean it's another thing. But DNA here, I am more on the footing. DNA has fantastic electronic properties as such. Is usually used for code assemblance, you can say, but they had fantastic. It has fantastic electronic properties, or electric. Now it's not about electronic, that I know of and that we calculate, but a piece of DNA has a lot of electrostatics properties, even magnetism. I mean, and that's on the large scale. So it can also be it can be a semiconductor. So it's when I said superconductivity is a different matter, but I mean it can be a semiconductor, it can be an insulator also.
I think you're both great philosophers. You're actually thinking about what the hell is going on, both of you. So what is going on between philosophy on one side, the thought process of us wanting to find out what is consciousness, what is life, why the hell are we here, all the big questions, contra science, because that is your wild dreams. In my opinion, wild dreams is to figure out what is it all about. And physicists, usually the great physicists, they're always great philosophers. So first Holger, what is your philosophy?
Yeah, I think maybe at this point I should mention this concept of emergence in general, because because I think when you ask this kind of things about life and consciousness and so on, we would immediately say, this is something that is emergent. So you have some system which is a physical system, and then you find that this develops some structures which you can talk about in another language, and then you can say it's something emergent. And the most simple case of emergence, to give the abstract definition of such emergence, that is when you see the animals in the forest, deers or so, and then you find out that they come in flocks. They come together. So you suddenly have a concept of a flock of deers instead of just single deers. And you can define a flock of deers, and you can begin to talk the language that this is a flock of deers, and here comes another flock of deers, and then maybe there are a few single deers around, but that is first approximation almost not happening. And in the same way, you could get some organized systems of enzymes or of molecules which could somehow make some system going along them that they could produce more of the same. And you could get some kind of, not a simple flock of proteins or whatever it might be, but you could get a flock consisting of several different types of them in a very organized structure. And if they are very good at their organization, they might function as a living system.
Yeah.
And you would think that life started in that way.
Yeah.
Somewhere.
What I hear from that is that what you say is that your philosophy is that matter, like physical matter,
yes,
structures,
yes,
consciousness. Because
at the end, even consciousness.
The emergence goes up in
but that's sort of several levels. That is like having flocks or something like that.
Exactly.
That is several levels above.
Yeah, I get that. Do you agree in that?
I think it's very beautiful. I'll first say that I've been bitten by a crazy or mad mathematician, in the sense that I always want to see mathematics, even though I was not that good at it. It's everything is I grab to mathematics. This is my existence. So when Holger says that, I immediately see a spin correlations, because the deers are running suddenly in one direction. I think it's very beautiful. This is there's a line of direction, or there's a direction exactly like the DNA has, of course, a 5 prime end and a 3. I mean, a beginning and an end, and the same with there's a spin up and there's a spin down. I mean, so if you line up spins in one direction, you get this emergence, and that's very beautiful, I think. But I am. You say we are philosophers. I say we are, first of all, the meaning of the book is to toss out a lot of mathematics and say, please put it together. It is. This is my understanding, but Holger has perhaps a higher level of understanding. He is truly even though he's a mathematical a prodigy or a genius, then he is perhaps more of a philosophy dreamer. So you see that thing. I see that they can merge together. Things can merge together and produce a coherence effect, and this is essential for life processes. And now we say this rearrangement is a good word. It was accidentally from me is a quantum rearrangement. Is Holger, is a fantastic thing. It can be.
Could you define it? You claim it's a good word. Could you define what you mean or think of by this quantum rearrangement?
Yeah, this is a thing that is possible when it's protected from quantum fluctuations, because then it's all averaged out again. What I say rearrangement is that you can build up some larger structures of spin in one direction. Say,
like in a ferromagnet.
Yeah, in a ferromagnet.
Both of you know that I'm crazy too, okay?
Yeah.
So when you talk about rearrangement,
yeah,
I say, okay, in the quantum level,
yeah,
yeah, everything is happening by chance. This is like what we know. It's random. It's random.
It has Holger, and we must accept here. I mean, and you were skeptical the other day when I talked about it, but quantum can be very ordered, exactly like chaos can also be ordered. Yes. But there are certain
it's old school to say that quantum mechanics is by random.
But yeah, it is some point there are quantum fluctuations, but there are other things that point to Ehrenfest theorem and so on. They point to the wave function is a distribution, and it's we all know that, and there are quantum fluctuation in that. But the central part of it is moving in a deterministic way.
Wow, I'm really happy for that, because I never believed that quantum mechanics was by random. I never believed.
No. But I mean, even when you go, I mean, if you use the Schrödinger equation, then formally this quantum mechanics is deterministic. But what is not deterministic is when you make the quantum measurement, then it is supposed that you get a distribution that is fundamentally random, in the sense that you only get probability answers out of quantum mechanics for what you measure. And in that sense, there is perhaps even a total fortuitousness that it is not. It is really random and statistical.
It is random in a sense that, let's say, one thing that people really don't like is that you measure a neutron, and you have this Stern-Gerlach magnet, and the neutron can go one way or the other depending on its behavior, I would say. But you can have half a neutron going one way, and you can have half of a neutron going the other way. Because when you end up, you have seen something that comes from both sides, and you have a restoration of a neutron. Holger, that. Yeah.
Okay,
no, you can make this kind of interference experiments with neutrons in Stern-Gerlach experiment, very much like the famous experiment of a two-slit experiment, where you send some particles through two slits and then measure interference on the screen behind.
Yeah.
So you can simulate that by neutrons in Stern-Gerlach-like experiments and so on. So there are many cases where you can see interference. And that, of course, is in a way, by definition, impossible to explain classically.
Yeah, because you have one, you can go down to one part.
If once you have this, that it is going in your best classical approximations along two ways, then it is not tolerable classically. So there you have a quantum thing.
Okay, great. Now I'm so confused. I think that there will be a chance that I will read the book from start to end.
Oh, but the book that does not answer all these things, Holger. I mean, we are terribly...
I'm afraid not. That's too much to require.
So listen now. Listen now. I don't know if this thing about what came first, the hen or the egg, is an English expression, but in Danish we have this expression: what came first, the hen or the egg?
Yeah.
Yes.
So all the religious people, they say, oh, God created everything. So that was the hen kid that came first, right?
Yeah.
And the egg is then the materialistic thing that we experience. All the materialistic guys says, oh no, it was the egg coming first. And then all our consciousness came afterwards. So there's an endless discussion. What came first, the hen or the egg? So my question is, has any of you considered that maybe life and consciousness and matter came at the same time? Stop the discussion. Could it happen that it was at the same time?
No, but Holger, there's one thing that is actually great here. I tried to say it before, but when it's this is this thing about determinism and what comes first and so on. And my God, quantum mechanics can be a split out, a decomposition of other states, and it's a terrible thing that either it can be. The egg that comes first, but the egg is made by the chicken or by the hen, and therefore therefore it is a little bit like quantum mechanics, that it's split up of different states.
Completely confusing. You go in circles.
No, but I mean, if you...
Therefore you cannot say what is first.
Well, I don't know. If you take the philosophy or the belief that somehow life maybe appeared on the earth, which means less than 4,5 or 4,2 million years ago. Then, if you believe also in our understanding of the early or the later, just after Big Bang, or few minutes when the lithium and the helium and the hydrogen was formed and so on, and you check it in the stars and so on, which was supposed to be 13, something million years ago. Then I think you have come to that there are some empirical evidence or theoretical evidence that matter from which finally life is built came earlier than the life.
Exactly.
And therefore...
And you explained that beautifully before by emergence.
Yes, exactly. This matches with the emergence picture.
I know Holger. Holger, he's a complete atheist.
Well, I don't know. Atheist is different because God is a little different from life. So I think life is one thing, and God is another thing. And I'm not sure you should count God in that sense as belonging to life. So this is not completely clear question, at least.
Okay.
And also he may be timeless because he created perhaps the concept of time. So this is more difficult.
Exactly. So, but you think the hen came before the egg?
Maybe in that terminology, yes.
It is true that there are some elements, and they build up into some. There comes some emergence of patterns. And these patterns is what is life. I mean, it's once it gets going by DNA or by RNA, then it's then you get going, and then it can sustain itself.
What then about entropy? We have entropy. Chaos becomes more
entropy.
Chaos.
Yeah.
More and more the time.
More and more chaos, but we see more and more order.
Not on the molecular level. I mean, if we believe in the second law of thermodynamics, whenever you make order in the office or order in the structure of the animal or so, there's supposed to be on the molecular level or on the micro level a much bigger disorder so that it is compensated. So whenever I would clean up and bring some book to the shelf to make more order, then I will use or create as much entropy in the molecular level as I'm bringing down the entropy of the books.
A little bit more.
Yeah, a little bit more in principle.
So
Just more. It's an inequality. But in practice, my suspicion is it will be much more.
But this is an essential thing in Einstein's early papers, and they have not been perhaps appreciated enough. But Niels Bohr and others were, and they both agreed very much on the genius of Gibbs, but what they were very interested in, or what Einstein was very good at, and what he found very essential, is that the entropy is a state function. This is the big thing. It's a state function, and then you can talk about whether entropy is increasing or decreasing, and that's important. It's dependent. The state function property is important, exactly like the energy, the various forms of functionals of energy, and therefore the entropy, we cannot change that thing. It has to be the classical way. Also on the quantum level, I mean, entropy is what it seems to be an essential thing, like conservation of energy.
Okay, so to end it off, why should people read this book?
People should read the book to get some inspiration, and simply to see how crazy things can lead to something. Therefore, they have a lot of formulas at the end of the book, so they can say they can put that together, they can put other things together.
Great. Holger, why should people read this book?
Yeah, I think this is a sort of good question, but they could, they might learn also about how these things are being thought about. And we have had a little bit this philosophical discussion. I think normal curiosity for philosophical discussion and so will ask you to get understanding of these things, and then you should see some of the ideas on the market. Now, it is of course strongly biased to be ours, but that they don't have to read only that book.
No, it's a lot of other people. But you're right, this is a semblance. This is to construct things. I mean, from some ideas here and there, some of them crazy and so on. This is to build up, yeah.
Thank you very much, both of you. It was a pleasure.
Thank you.
Thank you. And that gives surfaces. Yeah. And if you choose a little bit appropriately the density, then you will get a surface around the molecule. Yeah. Now you can compare, in principle, the surface of that, whether it smoothes onto the next molecule.
The curvature can be seen here and there where the grooves are, but that's not enough. I need to have the full topological, you can say. So what I have done up to now, and this has given considerable success in biotechnology, is that we have done enormous calculations of quantum mechanics. The biggest thing in brain science, in neuroscience, is to find out where these famous receptors, like we are so dependent on the dopamine receptor and so on, where the dopamine drug molecule, you can say, or the dopamine molecule, where it binds to the big receptor that is sitting in the membrane of some neuron.